Hey guys, this is my Unit 6 video over molecular geometry and polarity. So, when we're talking about molecular geometry, I'm talking about the way that the atoms are arranged around the central element. So, if we're looking at, let's say, the linear model over there, the lighter blue is your central atom. That would be, in the example of CO2, that would be your carbon. Now, your carbon has two bond pairs, and the bonding pairs are the two darker blue, which would represent the oxygen. Now, if we're talking about CO2, it's going to form that kind of a linear shape. And because it's a linear, as y'all know from geometry, it is in a straight line. And that straight line is going to measure at 180 degrees. So, with trigonal planar, it's the same general thing. It just has three bonding pairs instead of two. And because it has that third bonding pair, that gives it an angle, because circular is 360. So you divide that by 3, and that gives you a 120 degree angle between bonding pairs. And the reason that degree is so perfect and always will be is because when they bond, the bonding pairs, they just don't want to be near each other. And because they don't want to be near each other, they're going to push as far as they can, and it's going to give it that perfect kind of distance between them. And because they push, they're going to push against each other, and they're not that way they don't come too close to one, or they don't go too far. It just stays right there at that 120 degree bonding angle. Now, the tetrahedral, it's kind of like a trigonal planar in a sense, but it's set up with four bonding pairs. And because it has four bonding pairs, it forms a 109.5 degree bonding angle. And tetra is the prefix for four, so tetrahedral, four, same with trigonal, tri, three, obvious. And so because there are four bonding pairs, that's going to, like I said with the trigonal planar, that's going to force them to form that 109.5 degree bond. So if we're looking at trigonal pyramidal, it is not the same thing as tetrahedral. It's in the electron group geometry. It is in tetrahedral, but it is not tetrahedral. Molecularly geometrically, I guess, it's trigonal pyramidal because it is at 107 degrees for its bonding angle, and that's because that little like bubble thing you're seeing that looks like it's got a ghost on top of it, that is a lone pair. Now, the lone pair isn't connected to anything. The lone pair, it's just there. It's because all the electrons that are configured, or that are given towards that specific compound, that lone pair is just there. It doesn't have a bonding pair to bond to a central atom with. There's nothing there for it to do, so it just kind of sits there. And because electrons, the way they're set up, they have that negative charge, so that's going to force everything else. Instead of forming a tetrahedral, that's going to force them down, and that's what's going to give that 107 degree shape, or bonding angle, I'm sorry. Now, if we're looking at bent, it is also a tetrahedral, meaning it has four total electron groups. Now, electron groups are the total just number of groups of electrons. There's no simpler way to put it. And the way bent works, it's like a linear, but think of it as a linear with two lone pairs. That's exactly what it is. It's because the linear structure, they can't push against it because the electrons are negatively charged and opposites are going to repel. So when you have those two lone pairs, as you can see in the graphic, they push it down, and they give it that 104.5 bond angle bent shape. So here's a chart over the bond angles, if you're wondering more about them. Disregard the trigonal bipyramidal and the octahedral. I borrowed that chart from a YouTube video that I will link in the description, or the description of this YouTube video. That way y'all can go back and watch that one. It was basically pretty simple. Now, let's see. What's next? Okay. So, your bond angles. Those and your not your bond angles, I'm sorry, your molecular geometry, that influences your polarity, because if your molecular geometry is not asymmetrical, meaning if it is symmetrical, no matter the overall charge, it's going to be nonpolar. If you look at the third graphic over there with the hydrogen chloride, for example, it's polar because it has that overall net charge, or that net dipole moment. And excuse me, I'm shuffling notes around. Because it has that net dipole moment, that's going to allow it to have an overall charge. And if it doesn't, a net dipole moment is kind of like, you can think of it and remember it in a way as all the electrons. I like to remember it with hydrogen chloride because hydrogen is so small and chlorine is just massive. And chlorine is going to be, you can think of it like like a big dude. He's going to want all that food. Think of the electrons like the food. The hydrogen, it's skinnier, so it's going to have some leftovers, and all the food's going to go over to chlorine, and chlorine's going to take all of it, meaning it's going to make it kind of go like this charge-wise. It's going to take a dip because chlorine's heavier, and chlorine is going to be overall more negative, not hydrogen. And that's also what that symbol there is. With the arrow thing, sorry, I gotta put this up. No, that's not it. That one. Okay, so that arrow, I also use hydrogen chloride for this graphic. That arrow is showing a net dipole moment. It shows the direction that the moment is going to occur in, which in this case is going to be towards a chlorine. And because you have the delta negative and the delta positive is on the chlorine side because the moment is occurring towards chlorine. It's going to make chlorine more negative than hydrogen. And because all the molecules are going to go from hydrogen over to chlorine, hydrogen is going to be positive. It's weird. It doesn't have electrons, so the protons and the nucleus become positive. That simple. Chlorine, big dude, bunch of food, gonna make the whole structure, because it's linear, do this. And when it does this, it's negative. It becomes negative on the base, polar on the top, big dude's taking all our electrons. So, and oh yeah, so if you want an actual definition of polarity, here's Hank Green to describe that. Oops, sorry. Okay, here's Hank Green to describe that.
If that's the case, the outer electrons spend enough extra time around the element that's more electronegative that chemists label the molecule polar. The result is a partially negative charge on the more electronegative part of the molecule and a partially positive charge on the less electronegative side. Now,
so yeah, that is something I forgot to mention. Electronegativity. It's basically how bad that that element wants the electrons. So chlorine, he's a big dude. He's gonna want all that food. I kind of touched on it. I just never gave it a name. Hydrogen, small dude, doesn't want the food as much. It wants 2 burgers. Chlorine wants 8. There you go. Chlorine wants the octet of burgers. Hydrogen wants 2. Hydrogen gets 6 burgers. Chlorine only gets 2 burgers. Hydrogen's kind of going to look at them and go like, okay, so I'm going to give you everything to give you 6. Well, I have my 8, so let's share those last 2. There we go. We have an octet. We're all good. But then chlorine's going to, because he's bigger, he's meaner, he's just chlorine, he's going to attack hydrogen in a way, take his electrons, and that's going to cause the hydrochloric acid to be that just aggressive, nasty stuff that we know. So yeah, and if we're talking about electronegativity, as you see with this graphic, courtesy of Hank Green, I borrowed that from his video as well. It is the way, kind of, what the heck? It's the way, sorry, my phone's going off. How bad something wants it. And it's kind of, this graphic is kind of showing the difference in electronegativity between elements. So if it's a pure covalent, it's got 0. If it's a polar covalent, it's got low. And if it's an ionic, it has a high electronegativity. If you're looking at a periodic table, I didn't grab a graphic of this. I wasn't planning to go into this much detail. If you're talking about electronegativity, and you're looking at a periodic table, you've got your fluorine and that stuff up here, that's going to be the most electronegative because it's just the way the trend works. It's the higher you go up, the more electronegative, and the further this way you go across, the more electronegative, and both those peak at fluorine, making fluorine the most electronegative of all of them. So, it's to sum up polarity. Oh yeah, and electronegativity must be 0.5 or greater for it to happen. So if it is not 0.5 or greater, there's nothing there. It must be an asymmetrical distribution of electrons around the molecule. Linear will always be polar because it is asymmetrical with a bigger element. That's not right. My bad. Linear structures, as long as one end's heavier than the other, will be polar because they're going to do this. If you have something like the tetrahedral there, the carbon chloride, or carbon tetrachloride, yeah, I think that's right. It's going to, because the way it's set up, it's completely symmetrical. You can cut it in any direction, it will be symmetrical. So because it does that, there's no way for it to have a net dipole moment. It's shared all the way around, which means it's going to be nonpolar. It's not going to be polar. It's not. There's nothing there. It's just not going to be polar. And if something's symmetrical, it's going to cause it to just kind of, no matter what the charge is, it just voids it. There's nothing there. Now, the number of electrons in an atom also influences it because there was, I'm going to link the Hank Green video if y'all watched that. He touches on how he describes electrons as hipsters. It's weird, but basically if there's a bunch of electrons on an atom, it's the other electrons are kind of going to just not want to do with that because of shielding and that stuff. They're not going to be able to get to that positive nucleus, and they're just going to kind of do their own thing over here with another atom. So if there's like a bunch of electrons, it's not going to happen. So there you go, electrons are gone. Oh yeah, if a molecule is made up of the same elements, there's no way it's going to be polar. If it's made up of the same elements, they're both just going to share their charges. You can have 100 oxygens, and it's just going to be non-polar. There's no way. Now, if you throw one hydrogen in that 100 oxygens, it becomes 101 elements with that hydrogen in there. Then it will, I think, become polar. Even though that's probably never going to happen in chemistry. It should theoretically become polar because it's not, or has the opportunity to become polar because it is not the same element anymore. Yeah, so that basically touches on everything. Sweet. Yeah, took me like 30 takes to make this video. So, if y'all have any questions, ask me, ask Mrs.Zamzow, ask anyone. Watch the other group's videos, watch the Hank Green video, watch the video that I got the bond angles chart from. Watch them all, learn as much as y'all can. We're gonna have, yeah, I think Delaney's doing solids and Courtney's doing some other stuff, and we'll have a whole website thing set up for that, so y'all can go ahead and check out the rest of it for that. This has been Over Molecular Geometry and Polarity. Thanks for watching, guys. See ya.